Okay, so what do we got? We have a disk, we have something coming in and landing at some spot. What do I know? Okay, M and V and M and R for the disk. Oops, and then from the center is little r. Okay, so uniform disk sits at rest on a flat frictionless sheet of ice. The kid of mass M is thrown, okay, obviously the kid's a point mass, is thrown at speed v onto the disk, landing and sticking to the disk by virtue of, I don't know, maybe it's Velcro, as shown a distance little r from the center of the disk. So what happens to the center of mass after the kid lands on the disk? What? Yeah, the what center of mass. So once the kid is stuck to the disk, what happens to the center of mass of the kid disk system? After. Not during. After. No. After, not during. There's before. That means before. Then there is the during part, during the collision. That means like during. And then there's the after part, which means, I don't know what. Yeah, after the collision. Right, that part. So after the collision, what happens to the center of mass? It moves which way? That way at constant velocity. Why? Because there's no, not so fast. There are external forces. Very good, Faith. There's no external forces in the plane of the ice. There are definitely forces in the vertical, but we don't care. They're balanced. But no forces in the plane of the ice. Therefore, afterwards, the center of mass must move at constant velocity. That's whose law? Newton which? I see. Okay, one or two, something like that. Probably two. Okay, so we have, right. Now, where is the center of mass going to be? After, not fake, after the kid is stuck on here, we have mass of the kid, M, and we have the mass of the disk. So where's the center of mass of the combined system? Yeah, halfway, right? Halfway between a little r over 2. That's the center of mass. So afterwards, the trajectory of the center of mass is going to be this way. How fast? By inspection. Yeah, b over 2. Because the mass went up by a factor of 2. Momentum is conserved in the collision. Do I need to belabor this, or are we good? We'll say that's good. Okay. So now what? Is it just going to slide that way at speed v? No. Okay. It will rotate about the center of mass as well. How fast? So in order to figure out how fast, we're going to conserve what in this collision? Angular momentum. About what? Which point? Yes, cleverly chosen point. That one. I'm in favor. Along the axis of the kid's motion? Like what, the landing spot?
Yeah.
Okay, so then what's the initial angular momentum? 0. So what's the final angular momentum? 0. Okay, well, does it have any orbital angular momentum?
Yes.
How much? No. Orbital. Okay, so if we pick this point as our reference, then I'm in agreement L naught definitely 0. L final has two parts. R to the center of mass cross P center of mass plus I prime omega. What are our directions? Who cares? Why do we care?
No axes?
It's going to be into the board or out of the board, and I don't need to write, I just use the Cyclops or whatever, right? So what is the magnitude and direction of the orbital angular momentum? Well, with respect to this point, moving at speed v over 2, its mass is 2m, and the distance is little r over 2. And what's the direction? Into the board. So 2m times v over 2 times r over 2 n. Okay, well that must be equal to, plus whatever I prime is times omega, and I can deduce at this point omega must be out because the sum has to be 0. So all it boils down to in order to figure out omega must be, by the time I throw this to this side, it's negative in, which is positive out. So I can dispense with those signs. I have m v r over 2 out. Whoops, except that I'm wiping out the outs. And I prime. So I prime is just 1/2 mr squared, right? Because it's not rotating about the center of mass of the disk. It's rotating about that center of mass. So there's a hand here.
Is I prime omega out of the page because in order to get 0,
Yeah. Yep. So I prime, the moment of inertia for rotation about this center of mass is going to be two contributions. First, we have 1/2 mr squared plus the mass m times what? How far did I move the axis? Yeah, little r over 2, so I have to square that. That's the contribution from the disk. The contribution from the kid, m times little r over 2 squared. So that's a little r squared over 4. That's a little r squared over 4. So the sum of those is a little r squared over 2. So common factor of 1/2, and I have m over 2 r squared plus little r squared. And therefore, the final story is that the rate of rotation is, oh, I don't know how this became little m. Pardon that, it's supposed to be big M. How silly. Big M, V, little r, over 2, divided by, the 2 is going to go out because of that. So, clean that up. And the M is going to go out because of this. So clean that up. And I get r squared plus r squared. Okay, having done eraser physics, are the dimensions satisfactory? Yes. Okay. And are there any limits that we could take to check whether this has a snowball's chance in Minnesota of, what does that correspond to? What if little r goes to 0? That corresponds to the kid being thrown in the middle, so why would it want to rotate one way versus the other? And it doesn't, and sure enough, that works. Very good. Okay? Oh, yeah. Okay, we could have, right. So another place that might have made sense to choose as our reference point to simplify things, that was a pretty clever choice. That wiped out everything. Another one might be the position of the center of mass. And then we have incoming, but then we don't have any orbital to deal with afterwards. It's only spin. And it would give us the same thing. Okay? Questions? Yeah, Emily.
Why did L not equal 0?
Why did L, yeah, because, okay, I was using this origin, right? Okay, and so what's the initially the disk isn't moving, the kid is coming in, and the momentum of the kid, P for the kid is right along the line that passes through that point, so there's no perpendicular distance. So L naught would be R cross P for the kid, and actually when the kid lands there, R is 0. Yeah, you.
I'm trying to change the angular velocity as a linear velocity. What's going to be the R?
Okay, I'm going to try to repeat that question to see if I get it right. So if you wanted to translate the angular velocity into a linear velocity, what R would you use?
Yeah.
As in if it were rolling without slipping?
I think so, yeah.
But it isn't.
Yeah.
Yeah, there is no R that I would use because the center of mass is translating at constant speed and it's rotating about the center of mass as it goes.
So
Yeah?
how do you know that's not slipping or not?
Well, it is sliding on the ice,
Oh, okay.
right? We're looking down from above. Bonnie. She asked, what about the tangential velocity of what? A point at the edge of the disk?
Yeah.
So, okay, so I picked this point. And I want to know what? Okay, so what would I use? From here to there? Because it's rotating about the center mass. Awesome.